Hello, my name is Adrian and I work for POST Luxembourg. Today I'm going to be talking to you about our experience with the Resource Public Key Infrastructure, or RPKI. We started looking at RPKI towards the end of 2020, and we wanted to put this technology in place to increase the quality of our internet service offerings. As reliance increases on cloud-based and VPN services, customers are not only looking for reliable connections or redundant connections, but also quality, clean routing to go on top. Another reason as well is we'd been asked by customers when we were going to put this in place. Let's just remind ourselves of the original problem that RPKI is trying to solve. If we receive two identical prefixes in our network, but they come from different ASNs, we can't tell which is the genuine one. BGP can't help us with this. We need another source of information. So within RPKI, we have ROAs, Root Origin Authorizations. So these are statements by the resource holder linking prefixes and origin ASNs. So for example, on the right, you can see one of POST's ROAs. You can see our prefix and our ASN. There's also a maximum length attribute as well. So this means you shouldn't see a component or a subnet of this prefix that has a longer mask than /21 in the internet. When compared to this ROA, that subnet will appear as invalid. This ROA is signed by POST, so it's signed by our LIR certificate. So in a way, this is a bit like a signed root object, except that the data is of better quality. As I say, it's signed, and it's also centered around the 5 regional internet registries. In the global internet routing registry, we've got many databases now, some operated by commercial entities, some by service providers, and so the ROA information is of a higher quality. So there's two main parts to RPKI. The first part, on the left, it's all about signing our resources. So creating these certificates that link together the prefix together with the originating ASN. And this is based around the regional internet registry hierarchy. The second part, on the right, is then about using this information to validate whether our routes are valid or invalid in the network. So for this, RRDP is used to download these ROAs from the registries into our local network. The information is stored in cache validators, and the cache validators look at the certificates and check that the certificates themselves are really valid. We then use a more lightweight protocol, RPKI or RTR, to transfer this information to the router. And then the router will compare this information to the routing table to see which routes are invalid, valid, or perhaps there's simply no information about certain routes. So now I'll go on and explain what we did in terms of POST for the signing part and then for the validating part. So there's two ways that ROAs can be created. The first is the hosted option. This means that the regional internet registry hosts the database, they host the certificates, they take care of certificate renewal, and they provide a dashboard to administer your certificates. The second is the delegated option. Now this means as an LIR, you host the certificate authority yourself, you sign your own certificates locally, and you maintain the environment. At POST, we use the RIPE hosted option. The dashboard is straightforward and easy to use, and there's even a link to the BGP internet routing table. So you can see the routes that you're advertising onto the internet, you can select your routes and just make an ROA from them. For end users which are not LIRs but have also got resources, there's also a wizard as well for you to sign your own resources. So in terms of validators, we looked at three. Firstly, the Routinator 3000 from NLNet Labs. Then Cloudflare software, Octo Rpki and GoRTR. And lastly, Fort by LACNIC and NIC Mexico. So to start with, we worked purely in the lab. We used test routers and route generators, and we looked at each of these validators. We were interested in how easy they would be to set up, to configure, to monitor, and how we could do things like add exceptions locally as well to create our own local ROAs for particular cases. After testing, we decided to go with the Routinator. It can be used in a single Docker container. There's good status information available through the web interface and a straightforward configuration file for customizing the setup. So once we had selected Routinator for our validator, we then created two instances and connected them to our production network. So more specifically, we established these lightweight RTR sessions between the validators and our border routers where the upstream connections are. We also created a link to a local copy of Bird for testing as well. Now at this point, of course, we're not filtering any routes. We're just comparing the Rpki data against the internet routing table. So when you actually start monitoring, of course, we found there were plenty of invalid routes that were there for completely genuine reasons. For example, if there's any type of black holing or DDoS functionality, of course there are going to be host routes for this which are injected into the network, and these are more specific than are defined in an ROA on the within the registry, so these show up as invalid. Also, if you're using any private AS numbers internally, of course these don't match the origin ASN in the rower, so they appear as invalid too. Prefixes are going to be subnetted internally, so again these are going to show up as invalid. You also have to consider how IBGP treats routes as well. On some systems, depending on how you've configured the sessions as well, routes learned by IBGP might automatically show up as valid, even if they are actually invalid. So as I mentioned on the previous slide, using a copy of Bird was quite convenient instead of always issuing queries onto the live platform. Bird's quite flexible for this, and it was pretty useful to have this in place. Now, in terms of activating or filtering invalids, there's two ways of doing this. And when I first tried this in the lab, I globally activated filtering on the router. But this wasn't really such a good idea, because if you do this, all your exceptions have to be covered as ROAs in your validator. And as I mentioned on the previous slide, there can be lots of exceptions, and the validator then becomes critical for these. So it's not a very flexible approach. The second way I tried to do it is creating policies for each EBGP peer. And operationally, this is much more granular, this is much more flexible, because you don't need to add any exceptions to your validator then. You can have invalid routes in your network, but if you know why they're there, that's okay. And of course, if the validator fails, it doesn't impact the production traffic. With policies as well, you can also do other things like, instead of maybe dropping the routes, adjust the local preference. Communities can also be used for sending the state to other internal IBGP peers. At POST, we will activate invalid route filtering on our T1 transit services first, and then on the peerings afterwards. So what lessons did we learn from Rpki? First of all, build up your experience. Create a lab, play with the validators, play with some test routers, and see how it works. Check the invalids in your network. You'll probably find some surprises about where some of them are coming from. The RIPE training is really good. There's a 2-hour session that you can register for or simply watch one of the videos. Also, Rpki, read the docs. This is an excellent resource as well if you prefer reading. In terms of the Routinator, there's a Discord discussion server. There's lots of people who are willing to help you there. And also, train your team. You're putting this in place, but you need to explain to everyone else why routes might be dropped. And lastly, probably stay away from the whitelist functionality in the validators. So here's a few statistics I took from our network at the end of September. The total number of invalid IPv4 routes I saw in our border routers was just over 4,000. However, a third of these, 1,300, were actually covered by another valid route from the same ASN. So this means that the max length attribute within the ROA isn't being set properly quite often. Another third of these invalid routes were actually POST internal routes, because of course the aggregates that we use are divided up internally, and so they appear as valid when compared to the Rpki database. So taking these 2/3 away, we're left with 1,300 invalid routes. The statistics on the left I took from the Rpki Monitor website, and it shows that at the beginning of October, roughly 32% of the routes in the internet are marked as valid. On the right, I did the same exercise with the routes that are being sent to us by our transit customers, and actually 39% of these received routes are valid. So we're just slightly above the average for the internet at the moment. On this slide, you can see that some of the large internet exchanges and the tier 1 operators have already been dropping routes for several years already. At POST, we will start imminently. We will start before the end of the year, as I mentioned on the previous slide, firstly by dropping invalid routes from the tier 1s and then moving on to our peering upstreams afterwards. The last point I would like to add is please sign your ROAs or encourage your customers to sign their ROAs. Unless you have these signed statements within the regional internet registry, you don't get any protection from Rpki. But as soon as you've done this, it's integrated into the whole system, so your routes are protected throughout the internet. Even if you're not going to filter routes, do validation yourself, simply having signed the ROA already gives you protection for your routes. Thanks very much for listening.